And how do we calculate this eigenvalue and the eigenvector? I give you a simple procedure. We're going to spend some time to do it. Step 1, you just write out this characteristical equation, which is the determinant A minus lambda I equals 0. And you solve this equation, then you find those roots, which are the eigenvalues. And next step, for each eigenvalue, you're going to look at the eigenvector V. You have 3 different eigenvalues, then you have 3 different vector V, we call the eigenvectors. And then all you need is put the particular lambda, let's say lambda equal 1. Then you replace the lambda equal 1 here, and we know it's going to be singular. That comes from the definition. So if you know it's singular, you're going to find the no-zero solution. Again, the key word for you to understand is the no-zero. Once you can get the no-zero solution, I get an eigenvector. And then you change to the next lambda, you do the same calculation, you're going to get another eigenvector. For the example I gave above, you get 2 of them. Let's look at the example above. Okay, here you go. For this mirror reflection, how we are going to find the eigenvalue and the eigenvector? Step 1, you just need the A minus lambda I, which equals the A matrix -1, 0, 0, 1, minus lambda times the identical matrix, and equal 0 as a determinant. That means -1 minus lambda, this is lambda, and 0, 0, 1 minus lambda equals 0. You know how to calculate the 2 by 2 determinant. You multiply the major diagonal minus 0 times 0. You get the cancel out the negative. Lambda plus 1, lambda minus 1 equals 0. The first solution is 1. Second solution is -1. That's 2 eigenvalues. How am I going to find their corresponding eigenvectors? Let me call this as A1, B1, and the other one, V2, equals A2, B2. You do it one by one. For the first one, then you plug in the lambda equal 1 to this equation here. If we put 1 is -1 minus 1 is -2, 0, 0, 0, and times this one should equals 0. That's a 2 by 2 system equation. Well, do you have any surprise? You find that this is 0, 0? Of course, that should be 0, 0, because we talked about that special, because make this singular means the rank equal 1. If it's a singular, you got one equation only, -2A1 equals 0, then A1 equals 0. You have a freedom. What about B1? B1, pick any number you like. Every number is okay except the one number. What is this number you should not pick? What number you should avoid? No, think about a minute. Let me select the A1 equals 0. You have no choice. The A2, how about the 1? Perfect. That's what we found in the previous example. Here, see? 0, 1. See, the B equal 1, perfect well, and the lambda equal 1. This is what we have. We call the eigenvector. What is the value you should not select? The only thing you should not select is 0, 0. If you select 0, means you don't understand. Well, that's it. The next one for the lambda equal -1, you do the same thing. Put the -1 to here. So -1 minus -1, of course, is 0. And 0, 0. 1 minus -1 is 2. You multiply the second vector. It should equal 0, 0. Homogeneous system. So your equation is 2b2 equals 0. Then the b2, of course, equals 0. How about the a2? What do you select? The easier, the better. But don't select the 0, please. That will be 1, 0. And when you have the 1, 0, you know it's just flipped to the other side. And it's still in the same line. So the second vector is 1, 0. Look one more time to understand it. Here you go. This is the 1, V2. And now the image is in the opposite direction. Simply tell you the lambda 2 equal -1. So go back, connect these two examples in the geometry and in the algebra. And understand this, give you a very good understanding of the eigenvector and the eigenvalue. Let's look at another one. Sometimes you're going to get complex eigenvector and eigenvalues. For this example, we do the step 1, a minus lambda I equals 0. What is the a? It's 1, 2, -2, 1 minus lambda times I is the identity matrix equals 0. Well, now I have 1 minus lambda and -2, 2, and 1 minus lambda. Well, to make it quicker, all you need is to subtract the lambda on the major diagonal. So if you observe, all you need is minus the lambda on the major diagonal. Make it equal 0. So you got the 1 minus lambda square minus -2 times 2 equals 0. Negative, negative make it positive. And then plus 4 equals 0. Well, now how you are going to get this square equals -4? You know, no real number multiply itself equal negative. So conclusion is you're going to get an imaginary number. So you get the 1 minus lambda equals positive or negative 2i. Then your lambda 1 equals 1 plus 2i. And lambda 2 equals 1 minus 2i. Now we need to find the eigenvector for each of them. The good news is you only need to do one of them, because you can observe these two numbers are conjugate. And then their eigenvector, if I call the eigenvector V1 equals A plus BI, A and B are 2 by 1 vectors, I guaranteed the V2 associated with the lambda 2 will also be conjugates, A minus BI. Just like spouses, if somebody married, they go to party together. So guaranteed that the conjugate will be the other eigenvector, so you only need to do one. You finish the job in this case. Let's do one. Let me first assume this equals C1 and C2. Then I have, let's consider the lambda equals 1 plus 2i. C1, C2 equals 0, 0. This C I did not write very well. Let me do it back. C1. What is the inside? A minus lambda I, lambda equals 1 plus I. Then 1 minus 1 is 0, it's negative 2I, negative 2. And the 2, 1 cancel the 1 is minus 2I, that's negative 2I. Well, you got 2 equations and the 2 variables. What we are looking for? We are looking for no zero solution. You do not want to put a 0, 0 here. That won't make sense. So what is this matrix again? Must be singular. That means you cannot possibly have 2 different equations. I will show you that's really the same equation. If we multiply the I to the first equation, let's see what we have. Negative 2I times I is going to be 2. I squared is negative 1. And then this is the same as this after you multiply I. When multiply I to the second element, negative 2 times I, put I is the same as this. So what I'm saying is these 2 equations are the same equation, different just by the I. Since you have the same equation, you only need one of them. Let's select the second one. Let's select this one. 2C1 minus 2I_C2 equals 0. Then C1 equals I_C2. To make it easy, let's assume you have a freedom, right? C2 equal T, but I want to make it equal 1. I don't need many. I only need 1. Your solution is really a straight line, but I only need 1 vector on the line. Then the C1 equal I, what I have? Then my vector V1 is going to be 1, and I want to write it like this. Make A and B are both real, and A and both real. I factor it out. Then I write this as my A, and this as my B. You check. It's still 1 and I. Now the first one is 1, second one is I. What is the advantage of that? Then I can think about the conjugate. What's the V2? I told you they come together. The V2 is simply this A minus BI. So we got 2 eigenvalues and 2 eigenvectors as we supposed to get.